let me take your mind off studying. I'll start. Overseers here. I'll begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and these students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So I have some things to show you. So we're talking about diagonalization, uncoupling, and eigenvector examples. So let's see. I'm going to start with definition. Suppose V1, V2, all through Vn is a linearly independent subset of Rn, and A Vj is equal to lambda j Vj for all j 1, 2, n. Then beta is an eigenbasis for A. And here A is, of course, a n by n matrix, okay? So that's not the best definition. Usually you announce what things are at the start and then give properties. I'm kind of doing the opposite, but okay. So a theorem that we should know about, and it's worth taking a second here to prove actually, is the following. So here's the theorem. If we have T, a linear transformation on Rn, and let's say the standard matrix of T has eigenbasis beta, same notation as above. So that would mean that T acting on Vj would be equal to what? It would be equal to lambda j Vj, right? And I mean, if you think about this, you could just as well say that T of Vj is lambda j Vj, right? I mean, if you want to set aside the standard matrix and just talk about the linear transformation itself, an eigenvector of a linear transformation is simply a vector that when you feed it to the linear transformation, you get back out a scalar multiple of the vector again. So we could define eigenvector for linear transformation in the same way we define eigenvector for matrix, all right? So there's that. If T has eigenbasis beta, then the matrix of T with respect to the basis beta is just the diagonal matrix with lambda 1, lambda n down the diagonal. So that's the notation for this. Moreover, T beta beta is equal to the inverse matrix of beta times the standard matrix of T times the basis matrix of beta again, right? So let me just throw out a little bit more terminology here before we walk away from this. What do I mean by, we'll prove this theorem in a second here, but what do I mean by diagonalization? What does that terminology mean? It means that you take a matrix, all right, and you perform what's called the similarity transformation, and it becomes diagonal. So this right here expresses the diagonalization of the standard matrix of T. So again, to say a matrix is diagonalizable, like in the abstract, means this. Definition A, diagonalizable if there exists P and P inverse such that P inverse AP is a diagonal matrix. All right? So I'm saying a few different things in this theorem. I'm saying that if there is an eigenbasis for the standard matrix of a linear transformation, then it's diagonalizable. And not just that, the diagonal form of the matrix for the matrix itself is formed with eigenvalues. All right, so let's get to it. So there's two ways to prove this, and I think I'll prove it two ways because I think both are instructive for you guys. So here's proof number one. So you guys tell me, what's the standard matrix? Well, not the standard matrix. What's the matrix with respect to the beta matrix of T? Do you guys remember we worked this out? What was it? We derived that this is equal to the matrix of coordinate vectors of the basis, right? So like T of V1 beta, and then you have like T of V2, the beta coordinate of that, and so forth and so on until eventually you get to the nth one, right? But by assumption, V1 through Vn are eigenvectors, right? So what are we looking at? We're looking at like the coordinate vector of lambda 1 V1, the coordinate vector of lambda 2 V2, the coordinate vector of lambda n Vn. But what is that? What is the coordinate vector? How do we define the coordinate? How's the beta coordinate system defined? Well, think about it, and you should be able to convince yourself that what we have here is lambda 1 E1, lambda 2 E2, lambda n En, right? See, because as I discussed with you guys before, with respect to the choice of basis beta, the ith or the jth basis element, the coordinate vector of that, is just equal to Ej, where Ej is the standard basis, right? In other words, a coordinate system, another way of looking at it, is it's a linear transformation which converts your non-standard basis to your standard basis. You can look at it as that. And then that's what? Well, that's exactly just lambda 1, lambda 2, lambda n, right? So there you go. But we also know what? The coordinate, remember our discussion of coordinate change? What did we prove? The formula for T beta beta was what? It was beta inverse, the standard matrix of T beta, right? That's everything I said over here. So here, this proof heavily relies on you remembering our discussion of coordinate change for linear transformations, right? Which you may or may not actually remember that stuff. If you do, this should make sense to you. If you don't, it should be fuzzy, all right? Proof number two will be a self-contained proof. So let's consider beta, which of course is V1 through Vn, right? And let's consider beta inverse. Let's give it a name. Let's just say you've got like W1, Wn as your rows, right? And if we look at, let us say, beta inverse times beta, right? And you calculate the ijth component of that. What is that? That is exactly Wi dotted with Vj, right? This is our definition of matrix multiplication. Do you guys remember? Like we do the ith row of the left factor dot product with the jth column of the right factor. That's how we calculate the ijth component of the matrix multiplication. But on the other hand, if beta inverse and beta are indeed inverse matrices, this is also equal to like the ijth component of the identity matrix, right? Which we have a notation for that. That's the Kronecker delta. All right. So in view of this, we can just straight up calculate, you know, the matrix of T with respect to beta beta. I still have to fall back on the, you know, the coordinate change formula, which we derived the other day. I don't want to work through that again. But you know, this is supposedly beta inverse standard matrix of T times beta, right? But let's see how that goes. To save ourselves some writing, guys, let's let the standard matrix of T equals to A. That way we don't have to keep writing bracket, 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 bracket. Less brackets. Okay, so this is like, you know, beta inverse times A times the matrix V1, V2, da da da, Vn, right? But we remember how matrices multiply? We can multiply A times that by just what? By, so we get what? AV1, AV2, AVN, right? That's property matrix multiplication. But what did we assume about V1 through Vn? We assumed that they're eigenvectors for A, actually. So by assumptions of the theorem, we've got beta inverse times, well, lambda 1 V1 all the way on to lambda n Vn. Which then, if you look at it, you've got W1 da 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 Wn times this thing, right? At this point, let us just calculate the ijth component of it. So using this, like what is the ijth component of T beta beta, what we got? So we're supposed to take Wi, right? And dotted with the jth column of this. What's the jth column of that, though? It's just lambda j Vj, right? But the constant pulls out of the dot product, right? And so what do we got? So we've got exactly lambda j delta ij, which proves that the matrix is a diagonal matrix with the lambdas down the diagonal. So here are two separate, well, I mean, they're kind of the same proof, but they look different, don't they? Yeah. All right, so example 1 for today. Let me see here. Where should I work this? I guess I can work it here. Example 1. Let us look at the matrix A equal to 0, 0, minus 2, 1, 2, 1, 1, 0, 3. Our goal is to find the eigenvalues and eigenvectors. All right. So what's our first thing we need to do? We should calculate the determinant of A minus lambda I, right? So that's the determinant of minus lambda, 0, minus 2, 1, 2 minus lambda, 1, 1, 0, 3 minus lambda. In this situation, if you see you've got a row or a column which is all 0 except for one thing, then you just must expand on that one, right? So, you know, you look at here like this, that just screams at me, expand on the second column. So, all right, so I go plus, minus, plus. I mean, listen, it doesn't really matter the sign, does it? Because we're going to set this equal to 0. So whether I got plus or minus here doesn't really matter. And then I've got the determinant of minus lambda, minus 2, 1, 3 minus lambda. All right, so that works out to 2 minus lambda times minus lambda times 3 minus lambda plus 2, which is 2 minus lambda times lambda squared minus 3 lambda plus 2, also known as minus lambda minus 2 squared times lambda minus 1. So I find, after a little bit of calculation here, eigenvalues are lambda 1, I'll say equals to 1, and lambda 2 equals to 2. All right? Let me introduce a little terminology for us here. This one has algebraic multiplicity of 1. This one has an algebraic multiplicity of 2. The reason I say algebraic multiplicity is that's the number of times the root 2 appears as a 0 for the characteristic equation. See the difference? It's not 2 because it's 2. It's not 1 because it's 1. That's coincidental. Sorry, I'm an idiot. Yeah, I find it more amusing maybe than you guys do, but anyway. That is not by design. I just stole this from a textbook. This is actually the examples in Anton's Applied Linear Algebra book, which is a nice book, although considerably more expensive than yours. Let's see here. And I do think Lay is pretty good for this class, so no regrets. So let's find our eigenvalues. So, I mean eigenvectors. So I'll do it over here. For lambda 1 equals to 1, I need to look at A minus I times U1, which is literally minus 1, 0, 2, 1, 1, 1, 1, 0, 2, I'm reading the rows, times my disposable variables U, V, W. I'm setting that equal to 0. Do we need row reduction for this one? I don't think so. Like, if you look at this, it's fairly obvious that that's a minus 2. The rows 1 and 3 are really the same equation, right? Rows 1 and 3 are the same equation. The middle row is a separate but different equation. So like a procedure to solve this is just take the last one. I get U is minus 2W, right? And then from the middle equation, I get V is equal to minus U minus W, right? So at this point, in my first move, let me just explain my logic, guys. There's theory here. And the theory says that the number of eigenvectors you can find is at most the algebraic multiplicity of the eigenvalue. So like if the algebraic multiplicity is 1, I will only find one eigenvector up to scalar multiplication. So I know that I should be able to write the solution in terms of one parameter. Another way of looking at this, I've got 2 equations that are genuinely independent and a third which is redundant. So I'm starting with 3 degrees of freedom. I'm getting rid of 2. I should only have 1 degree of freedom in my solution. So if I can find a parameter to write the solution in terms of, I'm done. Once I decide to write U equals minus 2W, I've chose W as my parameter. So at that point, I'm trying to write everything else in terms of W. So the middle equation, I solve for V equals minus U minus W. But I know that U is minus 2W, right? Which is also known as, well, W. And of course, there's also, don't forget, W equals W. Yay. Stupid, but important. So U1, which is UVW, is actually what? Minus 2W, W, and W. So therefore, I'm going to let U1, because I'm looking for a specific choice here, minus 2, 1, 1. So if I was to write the full instructions for this problem, the full instructions for this problem are find an eigenbasis for A. All right, let's find an eigenbasis for A. So there's one thing down. Now next up, we got ourselves lambda 2 equals to 2. Now here, we're going to look at A minus 2I, U2. And A minus 2I, that's going to give us minus 2, O minus 2, 1, 0, 1, 1, 0, 1. So as you can see, we have 3 equations, but really, Really, we just have one equation, right? This is the same equation triplicated, isn't it? So what does this tell us? You know, what do we have? What's the story here? We have one equation, 3 unknowns. So we expect that our solution set here has 2 free parameters, right? 2 free parameters. And essentially, like, pick whichever one you like, but I'm going to say W is equal to minus U. Listen, you'd be like, well, couldn't you say U is equal to minus W? Sure. You have choices, right? If you'd like to make this unambiguous, you may fall back on the row reduction in our insistence on writing the pivotal variables in terms of the non-pivotal variables. If we went back to that, then we would all agree on the solution set. But short of rigorously always insisting on row reduction technique for this construction of the solution set in standard form, different folks are going to get different parameters depending on which one you chose as your parameter, which one you didn't. And that's fine with me, because I don't want to put that on you. I don't want to force you to use row reduction on all these, because I think just ad hoc reasoning is like way faster for these. I don't know, maybe I'm wrong, but so there's that. That's that. What else? What else can we say? U is a parameter. What can you guys tell me about V?
Free.
V is free, right? So don't be the person who says V is equal to 0. V is free. So our U2 is U, V minus U. All right, so remember that null space calculation, null space basis calculation? This is kind of like that. So we've got one, I mean, these are actually null space calculations. Every stupid one of these is a null space calculation, isn't it? We're looking at the matrix A minus some multiple of the identity equals to 0. We're finding the solution set to that, and we're finding a basis for it. That is the null space calculation every single time. So anyway, but it's not the null space of A, it's the null space of an associated matrix is the thing, though. All right, so we've got 1, 0, minus 1, plus V times 0, 1, 0. So this gives me U2 equals to 1, 0, minus 1, and U3 equals to 0, 1, 0. We can say this: W2 is equal to the span of 1, 0, minus 1, and 0, 1, 0. So the dimension of W2 is equal to 2, and that is the geometric multiplicity. The geometric multiplicity of lambda equals to 2. What was the geometric multiplicity of lambda 1? Like if you up here, you get W1 span of minus 2, 1, 1. Well, this has, you know, the dimension of W1 is what? It's just 1, right? So the geometric multiplicity of the first eigenvalue is also 1. So for this example, the geometric multiplicity and the algebraic multiplicity are equal for both eigenvalues. When that happens, you'll get an eigenbasis. All right, so in this case, if we set beta equals to U1, U2, U3 for my eigenbasis, then if we worked out beta inverse A beta, we would get a diagonal matrix, and the diagonal would be this: 1, 0, 0, 0, 2, 0, 0, 0, 2. So in this way, we would have diagonalized the matrix. Yeah.
Could you repeat like what you said about like what equals what to get an eigenbasis? I didn't catch that.
Oh, what I'm saying is that if the algebraic multiplicity is equal to the geometric multiplicity for every eigenvalue, then the matrix is diagonalizable. That's just a fancy way of saying, like, let me explain to you why that is. So the algebraic multiplicity, the sum of the algebraic multiplicities will always be n, because we're talking about an nth order polynomial. Well, okay, I should clarify further. If the polynomial has real roots, all real roots, right? So if all the real roots, if you look at them, if you've got a 10 by 10 matrix, you have to have 10 roots if they're all real, right? And so if maybe some of those eigenvalues are repeated, but if they are repeated, we're saying that you have as many eigenvectors as you have the repeat. If that's the case, then you've also got 10 eigenvectors. And by the theory, which I haven't told you yet, those will be linearly independent. You can check it out. The trace, let me call this thing D. The trace of D is the trace of A, right? The determinant of D is the determinant of A. By the way, if you've already calculated the characteristic equation, you can calculate the determinant of A without further calculation, right? Think about this. In this calculation, if you want to find the determinant of A, what would you do? How do I make this become A? I just do what? Put lambda equal to 0, right? Yeah? If I put lambda equal to 0, that makes that go away. I'm just determinant of A. If I put lambda equal to 0 here, what do I have? I've got minus 2 times, well, yeah, excuse me, that's 4 times, so minus 4 times minus 1, which is 4. Obviously, the determinant of this is 4. And we never have trouble calculating trace, right? Trace 0 plus 2 plus 3 is 5. 1 plus 2 plus 2, 5. And so that's a good check. We can always look at that as a check on our calculations, for one thing. We know that that has to happen because when we use the properties of the trace and the determinant, the similarity transformation cancels out, right? All right, anyway. Yep, okay, I think those were the tips and tricks I wanted to share with you there. So in my next example, example 2, so example 2, we have A equals to 1, 0, 0, 1, 2, 0, minus 3, 5, 2. All right, so let me point out that means our eigenvalue lambda 1 is 1 and lambda 2 is equal to 2. And this will have, algebraic multiplicity 1, and this has an algebraic multiplicity of 2. Right? You can easily see that the determinant of A minus lambda I here is equal to minus parentheses lambda minus 1 times lambda minus 2 squared. All right, so at number 1, let's look at A minus I times U1. What's that equal to? Well, you've got 0, 0, 0, 1, 2, 0, minus 3, 5, 1 times UVW. So I'm trying to find my eigenvalue vector with eigenvalue 1. So if you look at this, you got yourself U plus V equals to 0. So I chose to look at that as V is equal to minus U. And then my second equation gives me W my third equation rather, gives me W is like 3U minus 5V. So that would give me W is 3U minus 5 times minus U, also known as 8U. So put this all together, my first eigenvector in terms of U is U minus U, 8U. So therefore, let's make U1 equal to 1 minus 1, 8. I just chose U1 equals to 8 because it's a choice. Again, I'm trying to find an eigenbasis for A. But we're going to find out it's not possible in this example. All right. Number 2. Let us look at the second eigenvalue. What's A minus 2I times U2? Well, that's going to give me minus 1, 0, 0, minus, whoa, dude, oh, my bad. I skipped ahead. 1, 0, 0, minus 3, 5, 0, times UVW equals to 0, 0, 0. And here, just to make sure that I'm not swindling you or anything, I'm going to drop back and use the, whatchamacallit there, the row reduction technique. Because if there's any disagreement about the solution set, the row reduction technique should you know, alleviate that ambiguity. So here, looks like my A minus 2I, right? Put a 0 on just for good measure. What we got? We've got 1, 0, 0, minus 3, 5, 0, and then I can get rid of the last row, right? But that is clearly row equivalent to 1, 0, 0, 0, 5, 0, 0, 0, 0. Oh, I forgot my last row of zeros. You don't really need that one, do you? Anyway, I'm putting it there just in case some of you rely on it. Anyway, so long story short, what we got? So the given equation is row equivalent to that. You probably could write down less, right? I think we could reasonably, if you really know what's going on here, some of you probably could look at this and go, that row reduces to that. Like, you know, maybe 3 steps. I think I wrote too many steps. My apologies. So then what? What's U2 equal to? Well, apparently, you've got U equals to 0, you've got V equals to 0, and W is free. So you got 0, 0, W. So there's only one thing you can't make W equal to, which is 0. And so what we get is U2 is equal to 0, 0, 1. So in this case, W2, big W2, this is the span of 0, 0, 1. And so this says to me that the geometric multiplicity of lambda equals to 2 is just 1. So we had a repeated eigenvalue of 2, but we only had one eigenvector. All right? There's a theorem, which is this. And I think this is the theorem I just told Emma. Well, this is in a different language. So here it is. A diagonalizable. If and only if there exists eigenbasis for A. So we did this, start a class. All right. Let me show you the other direction now. actually the calculation is very similar to what's right here. You might almost be able to see why a diagonalizable, maybe I can do that. Let's see if we can get away with that. Can you see why a diagonalizable implies an eigenbasis? So if A is diagonalizable, right, that means that there exists a matrix, let's call it beta, because any matrix you can look at in terms of its columns, right? So if you think about the matrix in terms of its columns, then suppose it's diagonalizable. To suppose it's diagonalizable is to suppose that, you know, we have an equation like this, right? And that this is equal to a diagonal matrix. But what does that mean? That means that if you multiply the matrix on that column, you get this, you know, you get multiples of the column vector. I can't, I mean, I was hoping I could maybe save myself a board of writing, but I guess I can't. I can't quite see it from this calculation. Fine. Rats. I try to only do proofs in here which help you understand how things work. So I think this falls in that category. I'm on the bubble of not including this proof in this class, but let me do it. Otherwise I'll probably regret it. So this is the other direction. So suppose A is diagonalizable. So suppose there exists P and P inverse such that P inverse AP is equal to, you know, D1 dn, zeros elsewhere. And let P be like P1, P2, Pn. All right? Then if you look at AP, it would be equal to what? It would be equal to, let me call this thing D. It would be equal to PD, right? But that would give us that, like, AP1, AP2, APN is equal to what? What happens when you multiply, you know, P times this matrix, which is like D1, E1, DN, EN? What happens when you multiply a matrix by E1? You get column 1. What happens when you multiply a matrix by E2? You get column 2. Right? Think about this. So when I multiply this through, I get like D1, P1, D2, P2, and so forth. Does that make sense? But what does that prove? Column by column, that proves that, like, A Pj is D sub j, P sub j. In other words, I can see that Pj is eigenvector with eigenvalue lambda j just equal to dj. But we're assuming that these are the columns of an invertible matrix. So they're linearly independent. Consequently, the columns of the diagonalizing matrix form an eigenbasis for A. That's the other direction of the proof. That's it. All right, there is another theorem which I should share with you guys, which I think I will spare you the proof of because I don't think I've got enough time for it today. Maybe we'll circle back and prove this another day. The proof is interesting, and I've got a calculational proof, but here's the theorem. If S equal to, let's say, V1 through Vk are eigenvectors of A with distinct eigenvalues, So lambda 1, lambda 2, lambda k, then S is linearly independent set. All right? So as an application, if you have a matrix that has n distinct eigenvectors, it's diagonalizable. Excuse me, if you have a matrix which has n distinct eigenvalues, it's diagonalizable. I mean, it's also true if it has n distinct eigenvectors in the sense of linear independence. That means you have an eigenbasis also. So like, I could not conclude in example 1 or example 2 that the matrix was diagonalizable just from like calculating the characteristic equation, because in both of these examples we had 2 repeated, right? So further calculation was required to find out whether or not it's even possible to diagonalize it, all right? So yeah. All right, so I have a few more examples for you guys today, believe it or not. But before I do that, I want to capitalize on the examples that we have today, because I want to circle back to differential equations for a minute. And I want to derive the formulas that we had before, okay? Because I just pulled the solution to the differential equation from the thin air. I want to show you how we can actually derive it, just using the solution which one of you guys told me from calculus 2. This actually is an easy calculation with everything we have now. Check this out. So let's suppose A is diagonalizable. All right, with eigenbasis beta v1, v2, vn. Then we know the story. Beta inverse A beta is equal to what? Lambda 1, lambda n. Diagonal matrix, right? Consider dx dt equals to ax. This is the system of differential equations with coefficient matrix A. Man, half the class wasn't here to see that. Rats. Then we're going to make a substitution. Y is the coordinate vector of x with respect to beta, right? A straight up formula for that is beta inverse x, which means, among other things, that x is also equal to beta y, right? Right? So what we got here? So we've got ddt of beta y is equal to a, let's see here, x was, beta y, right? But the thing is, beta is a constant matrix, right? A is a constant matrix, beta is a constant matrix, so you can pull it outside of the derivative, right? That's the calculus. Well, so we've got beta dy dt is equal to a beta y. Multiply this equation on both sides by beta inverse, and we've got dy dt is equal to beta inverse a beta y, which is what? That is explicitly lambda 1, lambda 2, lambda n times y1, y2, yn. And this, on the other hand, is dy1 dt, dy2 dt, dyn dt. So in this new system of eigencoordinates, our differential equation, which originally was coupled. Coupled means that the differential equation for x1 possibly involves x1, x2, x3, x4, all the way out through xn. The differential equation for x2, dx2 dt, involves x1 through xn. They're coupled. To solve one, you have to solve them all. These are uncoupled, because these In the y-coordinate system, we just have dyj dt is equal to lambda j yj, which you guys told me last time the solution is easy to find. Solution to this is just yj is equal to cj e to the lambda j times t. Separation of variables. Separate, integrate. That's the solution. That's true for all j. So my solution actually looks like, you know, C1 e to the lambda 1t, C2 e to the lambda 2t, you know, Cn e to the lambda nt. Right? That's my y. X was equal to what? X was equal to beta y, right? So that's V1, Vn. This is my beta matrix. What happens when you multiply that by that? You get C1 e to the lambda 1t V1 plus C2 e to the lambda 2t V2 plus Cn e to the lambda nt Vn. That is the general solution to the differential equation. And we didn't even need the theory of differential equations here to do it. All we needed was calculus 2, change to eigencoordinates, calculate. So changing to eigencoordinates uncouples the problem. That's why this works. And we can go back, right? Like example 1, the solution to this one, if I look at dx dt equals to ax from example 1, my solution is x is equal to c1 e to the t. What was my one eigenvector? Minus 2, 1, 1, plus c2 e to the 2t, 1, 0, minus 1, plus c3 e to the 2t, 0, 1, 0. Now for those of you who are in differential equations, you might feel like this is wrong because there's no t in the repeated root solution, but that is a wrong thought because this is not that problem. You can have a repeated root and not have a t times an exponential because the degeneracy of the 2 being repeated is repaired by the fact that you can have linearly independent 3-dimensional vectors. Those are genuinely different solutions. That's the solution. All right, so let me go on. Still got 8 minutes, right? All right, lightning round. Example 3. Here we have a is equal to minus 1, 2, 4, 0, 0, 3, 1, 7, 0, 0, 5, 8. Oh, that's right. They got some kind of hipster influencers in Convo today, don't they? Hey, Convo's not next. Oh, you guys still have a test after this, don't you? Example 4. A equals to 1, 0, 0, 0, 1, 0, 0, 0, 1. Example 5. A equals to 3, 1, 0, 0, 3, 1, 0, 0, 3. And then finally, example 6 is A equals to cosine theta minus sine theta, cosine theta. I'm going to tell you the story for each one of these. It's not going to take long. Example 3. This is diagonalizable. The eigenvalues are minus 1, 3, 5, and minus 2. Those are distinct, therefore it's diagonalizable. Right? It would take more calculation to actually find the eigenbasis, but you should see how to, it should be clear how to do that after you see the calculations we did today. Example 4. This is diagonalizable because it's already diagonal. What are the eigenvalues? 1, 1, and 1. What is an eigenvector for the identity matrix? In other words, this is the identity matrix, right? Check it out. Ix equals to x for all x in R3. So does that mean that all of R3 is eigenvectors for the identity matrix? It's a trap. The answer is no, because 0 is not an eigenvector. But ignoring 0, everything else is an eigenvector for this matrix. This one, you have lambda 1 equals to 3. So the algebraic multiplicity is 3, but the geometric multiplicity is just 1. Now, I don't have time to calculate that, but if you calculate this, you'll find that there's only one eigenvector. So there you have a three-peated eigenvector, but only one eigenvalue. And then finally this, our last example before break, is an interesting one. The characteristic equation here is cosine theta minus lambda squared plus sine squared theta. So if you set that equal to 0, you got yourself lambda is equal to cosine theta plus or minus I sine theta, also known as e to the plus or minus I theta. So this is not diagonalizable for an entirely different reason. This is not diagonalizable, usually, because the eigenvalues are not real. They're imaginary. What's the case it could be real? Complex unless what? Theta is like an element of, pi times, well, just say theta equals, let me be weird, less weird, theta equals to n pi for some n in an integer, right? If you put theta equal to 0, that's the identity matrix. If you put theta equal to pi, it's minus the identity matrix. But otherwise, that's not diagonalizable. It's a rotation, right? Think about that. Is there any matrix, any vector, that if you rotate it, it goes back to a scalar multiple of itself? No, right? So there's no eigenvectors for a two-dimensional rotation. What about a three-dimensional rotation? Oh man! Ah! Three-dimensional rotation, if I'm rotating around this axis, right? There's one vector which is an eigenvector for a three-dimensional rotation. Which is it? The axis vector. See, so finding an eigenvector for a three-dimensional rotation is tantamount to finding the axis of the rotation. Anyway, I'll shut up. Go away now.